Hey everyone, thanks for being here. I'm going to go ahead and get started. This right here is the HPF 24S6 power supply. If you come from notifier background, this is the FCPS style power supply. Firelight also has a version with yet another part number for it. They are all completely identical. They all use the same two transformers I have here behind the meter. The power comes in right here on these three terminals. So this is earth ground, AC neutral, and hot. That's where your power would land. So it'd be green, white, and black. These two plugs right here are important. A lot of times we take this circuit board out and we give the cabinet to the electrician for them to mount, install, and pipe. And we'll leave these transformers in, but we take the circuit board out to protect the circuit board. So when we're putting it back in, you need to make sure that both of these are plugged in, because these are the transformers that take the 120 volt coming in and they step it down to the voltage we use for fire alarm. Now, a couple other things before I get started. There's only a handful of tools that you need to do this. One of them, you can already see here, it's the meter. This is incredibly vital. Don't skip the steps we talk about with the meter. The other two is a typical screwdriver and some kind of wire cutters, wire strippers. I like these because they're like wire strippers, but they're a lot beefier so they can handle cutting and not get all dented up and tore up and everything else. So I'll continue giving kind of an overview of what we have on this circuit board, and then I'll get into trimming the wires. So I already started with the transformers and where the 120 volt will land. Down here, this terminal, we see the white square. There's two little silver pegs coming out of it. That's where your battery jumpers will land on it, and they'll come down, and batteries will sit down here on the bottom of the cabinet. Down here at the bottom, we have dip switches. This will handle all the settings of what our power supply does. This bank over here, we have our sync terminals here at the bottom, two screws. We have our input, our output, a second input, and then this is auxiliary power, the top two terminals. Coming across the top, these are our four NAC outputs. So you have output 1, 2, 3, and 4. These are the auxiliary treble monitoring contacts. They are just your normal common, normally closed, normally open. So if you're monitoring this panel with, say, a mini module for treble, that's where you would do that. And then last, but definitely not least, right down here, we have this row of LED lights. I'm going to go through each one real quick. The AC power, that's this green one. As long as the panel has power, that green light is on. If the green light's not on, then there's either something wrong with the board or you don't have power. The next one is the ground fault. If it's on, you have a ground fault. If it's not, you don't. Then you have a battery. And again, that's telling you if your batteries are good or not hooked up. Those will be lit up.
Sorry to interrupt you.
Hey, how's it going?
The other time that green LED light will not also light is if that panel's running on batteries. So you won't know that the panel's running on batteries unless you actually put a meter on there and check it out. So just to let you know. So I'm bailing out now again.
Okay. Well, thank you. So we have the battery light here. Moving on from that, we have the NAC treble. Now this one can be frustrating at times because it flashes to the number of times to correspond with which circuit it is. So one single flash means output 1 has a treble. 2 flashes means output 2 has a treble. But if you have a treble on multiple circuits, it's only going to flash the first circuit. I think it starts with 4 and then works its way across. So it'll only flash 4 times until you clear NAC 4. And then all of a sudden it might tell you that you also have a treble on NAC 2. But it won't do 4 and then 2 and then 4 and then 2 to tell you have 2 separate trebles. It'll only tell you one circuit at a time. And like I said, I think it works 4 has the highest priority, then 3, then 2, then 1. But I might have that backwards. It might go 1, 2, 3, 4. And then this last one is AC charger fail. Typically, if you see the battery and the AC charger fail lit up at the same time, there's a good chance your batteries are just bad. If you see the AC charger fail lit up all by itself, but the battery's not lit up and your AC light's on and all that's fine, then your batteries probably have enough voltage, but it's telling you something about your charger's not working. So you need to go into some diagnostic process of checking out, okay, is the charger on this thing still good? And that can be checked by putting your voltmeter across your battery, positive and negative, and seeing what it is with it plugged in. And then you pull it off right here, and that voltage should drop. If it drops, then that means your charger is indeed charging. And if it doesn't drop, which would likely be the case if that light's lit up, then that means your your charger's not charging and you need a new circuit board here. Oh, and then there's these 4 standoffs here. This is where we mount our control modules. I'll get into that here in a little bit. That's the overall layout. Now I'm going to talk about these wires I have pulled in here, and we'll get into where they actually go, how they wire up. So I have 7 wires that come down, 6 of them being red. 1 of them is green because I didn't have blue wire. But my green wire is our SLC that we normally pull blue wire for. I'm going to save that one for one of the last ones. Then I labeled them here. You probably can't read them on there because I can barely read these in person. It's my own handwriting. These 4 right here are my NAC circuits. So I have 4 NAC circuits we're going to have to trim out. And I have 2 sync circuits. So we're going to have to set this board up to be a NAC follower or NAC slave. And what that means is that there's another thing sending out a master signal somewhere, and we're going to tell this panel to follow that master signal. Now, before I get to stripping back and cutting and landing these wires, I want to talk about service loops. There are 2 ways that I've really seen these trimmed out. One is where you put your service loop inside the panel, and one is where you put your service loop up in the ceiling above the panel. I prefer the latter of those 2. I don't like it being in the panel when it comes later time to actually do service work on this. It makes it difficult to trace that wire and where it goes up the pipe and all that and out into the field. I find that the service loop up above the panel generally looks a little neater. It makes working inside the panel itself cleaner. The point of the service loop is if the board ever has to be changed out and you need some extra wire to work with, that loop's up there just to have some extra wire. So you don't necessarily need it right here all the time. It just needs to be available somewhere. For field devices like strobes, horn strobes, speaker strobes, smoke detectors, pull stations, and so on, the point of that service loop also comes in if a device has to be moved, like it's been installed, say, in the direct center of the room, and then the air conditioning guys come in and they drop an air vent right beside that smoke detector. We need enough wire that even though that device is already installed, we now have to move away to maintain a 3-foot minimum distance between the air diffuser and the smoke detector. So we need to have enough wire there that we could, cut a zip tie and move over somewhere so that we can maintain that code required distance. So the service loops typically provide, that's like their main function. So I want to just say, make sure anything you're doing, you're leaving a service loop. And the way I'm going to wire this up is assuming that there's a service loop up in the ceiling above this. Also, coming in right here where the wire's coming in, there should be conduit in a connector. I didn't run conduit in a connector to mount this on the wall for me to pull it down 30 minutes later. It didn't make sense to take all the time to deal with conduit. But just know there should be conduit here, and pretend that there is. I'm going to ask you to use some imagination. So we have a service loop above the ceiling and we have conduit. Now, that being said, I'm going to start with my NACs. Now, I didn't label these NAC 1, 2, 3, 4. They're all just labeled NAC, 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 and NAC. So I'm not going to worry about which order they go in. If they are labeled 1, 2, 3, 4, I like to correspond those with 1, 2, 3, and 4. So I like to correspond them with the numbers. Also, if I'm working with like 5, 6, 7, and 8, then I'll do output 1 is 5 and output 4 is 8. And, you can fill in the sequence from there. So I'm going to start with this NAC circuit here. Try to come and just untwist it as much as possible to keep it neat. And I'll come and I'll bend it over and I'll bend it again, trying to get nice straight runs. And I'll land it right there where I'm coming between these 2 terminals, and I'll cut it about where my finger is. So that gives me a little bit of wire to work with. So then I strip it back. You see you have a pull cord here. If no one's ever showed you how to strip wire, grab that pull cord, and anyways, you pull it back like this and it tears your jacketing for you so that you can trim that off. And now, just in case when you strip the wire, if you nicked anything around here where your strippers were, you have a clean set of wire. You have clean wires up here that aren't going to have that problem. So again, I just cut it like this. Strip these back. Not too far, but enough copper that I can land that underneath the terminals. I'm not going to land it yet, and I'm not even going to go to metering it yet, because what I like to do is I like to go and get all my wires ready to landing, have them all stripped back, and then I turn my meter on and I go do all my circuit metering at one time, and then I go and land them all, and I'll show you what I mean. So this might get a little bit boring here while I trim out more wires. Here's another NAC circuit. So I follow this over here, and I do Basically the same thing where I line it up right there in the middle. I just try to make nice, neat bends. So you see, I'm not leaving a lot of wire here in the panel itself to work with. And that's another reason that service loop up above the ceiling is very important. Because if something has to be changed, like say down the road, they swap it out for a different model power supply, this wouldn't leave enough wire to swap out for another power supply. And it might be you out there as the service technician. So having that service loop up there just makes things a little bit better, a little bit easier. And it kind of creates a backup. So that's just going to keep, that process is going to keep repeating. So I can put these here right now just to see, you know, just to hold them out of the way. But I'm not tightening the screws down because we're not done with them. Now with the next one, before I cut it, I'll show you kind of what it looks like when people put the service loop in the panel. And it's not wrong to do it that way at all. This is completely a personal preference. As long as you have a service loop, you're doing it okay. If you don't have a service loop, then you're doing it wrong. It's starting to take shape. You can kind of see how those wires are going to look in there and how they fit nice and neat out of the way. And they're not going to be bunched out, jumping out at you when you open the door to this panel. Here we go. Here's my last NAC wire. And so for a service loop, someone might make the loop and then they flatten it out like this up here and curve down to grab the terminals like that. So you'll see a bundle of wires across the top. And again, that's not wrong. You still have a service loop, but you have this bundle of wires. And if you ever have to come back and do service work and chase the circuit on this panel, you know, have to deal with that bundle of wires. So I'm going to continue doing it this way because it makes identifying the wires just easier. And landing the NAC circuits like this is fairly straightforward. The way you should wire up every single device is that the conductor here that's sheathed in the black jacket is going to be the negative side of our circuit, and the red is going to be our positive. And I don't think you can see it on here because this is not the world's greatest camera. But to the left, the terminal is negative. To the right, it's positive. This is kind of a prelude of what it will look like when it's all installed and tightened down. I'll be able to come in and straighten those out, kind of untangle this bit here and dress it up a little bit more, make it a little more professional looking. But we're on the right track here. So now that I have them all stripped back, I'm going to pull them up out, and I'm going to go ahead and show you what we're going to do to check our NAC circuits for with the meter. So I have 4 circuits here. They're trimmed out. You can see how they're all going to land on the panel. Now, I'm going to check for a couple of different things on each circuit. The first thing I'm going to check for is I'm going to check for end-of-line resistor. And if you remember back to our panel demonstration or our meter demonstration video we did months ago, that's going to use the ohmmeter setting on the multimeter. Looks like the Greek letter omega. And this is only to be used when circuits are not attached to a board. So you see I have them out here. They're not attached to a board. If I touch the 2 right here, that tells me it's a direct short. So I know my leads are working, my meter's working, and I'm going to just go each one. This panel uses a 4.6 K ohm resistor, so I should see something in that neighborhood on each of these circuits. This one sees 4.61. I'm sorry, it's a 4.7 K, so 4.6 is in the specified range. And again, 4.607. I have an open circuit there. I'm not going to go diagnose it. That just means I have a bad wire nut up there. 4.62. So if I land this on the panel, I already know that my NAC 2 is going to have a trouble because it's going to be an open circuit because I couldn't see the resistor with my meter. So this would be the point here where I would stop, where I could stop what I was doing, or I could finish trimming the panel. But before I power it up, before I start turning things on, I go and I start identifying where NAC 2 goes in the building, and I go and I chase it, and I find where my open circuit is, or I might just start by going to where I think the end of line is on this circuit. Hopefully I remember where it is and I did good as-builts or something. But go to the end of line device for this circuit and make sure the resistor is actually installed. That could be a real quick fix. If not, then you divide it in half and you check to see, you know, which way is your open. I have that video on the YouTube channel if you need to go back and remember how to troubleshoot a NAC circuit. That video is on there and we discussed that whole principle there. The other thing I'm going to check with the meters, I'm going to look for ground faults. Now, I'm going to be really confused if I have a ground fault in this because these wires just go up above the camera and they're zip tied up to the wall and that's it. They don't go anywhere else. So I shouldn't see any ground faults here. But you have your earth ground right here ready and available for you. But we're looking for continuity between earth ground and any leg of the circuit. And again, we've done a video on that. So if you need to go back and review the video on ground faults, that's on the YouTube channel as well. So one at a time, I'm just going to check each individual conductor. And as I expected, there is absolutely no ground fault because I didn't think there'd be a possible way to have a ground fault on this system, especially being that there's no wire coming into the earth ground terminal. Now, if this was actually wired up and I had an earth ground there and I was actually running wires through a building, then you could see where that would actually be able to pick up an earth ground. In this little situation, I was just going through the motions to show what it looked like. Hopefully my arm didn't get in the way and y'all saw how I actually just went one at a time and just touched each one of these conductors here so that I know there's no ground faults on any of these circuits. So now I know where my open and shorted circuits are, or I know they're not shorted. I know which one is open. All the others are clear. So I can go through and one at a time land these to the panel and actually tighten them down. It's pretty quick and simple to check it with a meter like that, and it can save you a lot of time, especially if you're waiting on the electricians to turn power on. Doing it this way, you already know that your circuits are going to be clear, so you're not waiting for power to come on, crossing your fingers, saying, oh, please, oh, please, oh, please, no problems. You're like, no, I've already done the work. Oh, I put that in the wrong one. You know, you've already done the homework. You know that everything is good. So when it comes on, you know that it should just come on a clear panel because you checked it with your meter. Also, doing this helps protect the panel, because if we see shorts or something else, that could be an indicator that there's some kind of voltage crossed over on this circuit that shouldn't be there, and that can keep us from damaging our stuff. So we can also fix that problem before we apply power to it, instead of sending power back into the panel. So there's our 4 NAC circuits. They're now trimmed out, landed on the panel. This right here is a bit long. I could cut those back and make it a little prettier, but this is the gist of it. So now I'm gonna come over and start addressing how we wire up everything over here. By the way, this black wire over here to the side, this is the microphone cable. I have the microphone up on top of this so that y'all can hear me. Otherwise it would be like halfway across the room and you probably wouldn't be able to hear me very well. So we have these 2 red wires and this green wire left. That's our SLC. The 2 red wires are our sync circuit. Now we have sync negative and sync positive down here. There's not an in and an out. So both of the black legs from our 2 sync wires will land under the negative, and both of the red wires will land under the sync positive. What a sync circuit is, what it does, this is where if you have multiple power supplies throughout the facility, we need them all to be flashing the lights at the same time at the same rate. It's supposed to help with epilepsy and that sort of thing and not induce seizures. If you have too many different lights flashing at different patterns at different times, that's supposed to be something that can cause seizures pretty easily. It's important that we, and code required, that we have sync throughout the building on all of our strobes so that we're not causing people to have seizures when they should be evacuating a building. This would be included in my service loop up top, so I just made it where the wires come right down. And I'm going to cut them all to be the same length. So a sync circuit will have one singular source. It can be the first power supply in your chain of power supplies. You can make one of the power supplies the master sync. If you're using any NAC circuits that come off of a main control panel, that main control panel will most likely need to be the sync master. A lot of control panels do not have terminals built into them for a sync input, but they do have sync output on their NAC circuits. Most of them these days, not all of them. So again, you see I've got the 2 black legs under the same screw, the 2 red legs under the same screw, sync negative, sync positive. So that's all it takes to wire up a sync circuit. Let's pretend that this is a NAC circuit coming off the main control panel, and its job is to be the sync wire for the facility. So that NAC circuit will just go and hit every single power supply. And this is all it's doing, is landing right here under these sync terminals. Then we will have to set up our dip switch settings down here. So I have this book here that tells me, see, here's the book, and there's just a table that tells me what each switch on the dip switch thing does. So I'm going to look at it. It says switches 1 and 2 work together to determine the strobe synchronization type. Now this is an old power supply that came off a job. I think it's actually bad, so I'm not going to power it up today because I don't think it's any good. It tells me that if 1 is off and 2 is on, that is set for system sensor strobes. So this is switch number 1 right here. This is switch number 2, just the first 2 from left to right. That's where you set what type of devices are out there. If they are both off, there is no sync. If 1 is on, 2 is off, that's Gentex. If they're both on, that's for wheel lock devices. So you have a few options of devices that can work with this one. I'm going to leave it with 1 off, 2 on because everything we install is system sensor. Switch number 3 is if this is configured as a slave or follower. If you turn switch number 3 off, which default out of the box, it comes turned off. It'll ignore whatever signal's coming in on here. It won't matter if you land wires or not if 3 is turned off. It'll create its own sync. If you turn 3 on, then it will follow whatever sync is coming from here. Switch number 4 is your delay AC fail reporting. I like to leave 4 up because that's for power loss. So if your building loses power, your fire alarm control panel is already going to say, hey, I lost power, AC power loss problem. If I've got 7 control panels on the job with the fire alarm control panel, I don't need 8 Trebles for losing power. I only need 1, so I let the panel do it. By leaving 4 up, it lets it stay for up to 2 hours before these panels start reporting. And at that point, it's reminding the customer, hey, not only have I lost power when I sent you that first signal, the power is still out because now all these other panels are still saying they don't have power. So I always leave that switch 4 up. Then 5 and 6, they work together to determine what these outputs up here do. So 5 off and 6 off, which is the default, that's general alarm. That means every single one of these turn on like a normal NAC circuit at the same time together. 5 off, 6 on is split alarm. So we have 2 inputs over here, so they can be, it splits them so that a couple outputs can go to one and a couple outputs can go to the other. So if 5 is on, 6 is off, then that is a split but temporal, where it's it's acting as if it is the master sync instead of being a follower off of that circuit. And then 5 on and 6 on is selective silence. And it says NAC outputs 1 through 4 are controlled by input 1. The sync input is ignored. Control input 2 determines when selective silence for all outputs will occur. So what that's saying is you have something coming in telling it, okay, we're in alarm now, and that's not going to be a silenceable trigger telling it it's in alarm. And then you have another control coming in. We don't really use that feature. 7, if you turn it off, or I'm sorry, if you turn 7 on, it disables the battery charger. And if you turn it off, which is the default setting, it enables the battery charger. And then 8, whenever you turn it on, it turns output circuit 4 into a door holder. So that's this one over here. And door holders work in the exact opposite function of a NAC circuit. Whenever everything is in standby mode, they are sending 24-volt power out so that they power the electromagnets that hold the doors. And whenever you put this panel into alarm, circuit 4 would then drop power, but circuits 1 through 3 would then activate power so that these turn on strobes, but this one releases the doors. So that is dip switch 8. So for this one, I'm setting it all up where all 4 of these are going to be your typical NAC circuits. They're all powering strobes, and it's following a sync signal. So we're going to have 1 down and 2 up for system sensor sync, 3 up to be a NAC follower, 4 up for that AC power delay, and then everything else turned off for it to be normal operation. So that's a really long-winded way to explain the dip switches. But that's how any panel that has dip switches works. You got to read through it, and you just go through it switch by switch, and you set it to what you need. Another note for dip switches, in order to get most panels, including this one, to accept any changes made on the dip switches, you actually have to power cycle the panel. So it's best to do it while the panel is turned off. Then you set your dip switches. And when you turn it on, then it sees what the switch settings are and it does whatever they say. Now, the last thing we have is this SLC wire and how we're going to trigger our input. So for that, we're going to I have right here the Gamewell one, because normally if we use these power supplies, we're doing it with a Gamewell system. This is the AOM 2SF. It's a control module like I talked about last week. So this one, first of all, comes with an end-of-line resistor. This resistor is spec'd at 47 k ohms. And then you have the module here. So our SLC lands on these two terminals. The top left require external power. So we're going to get that from our auxiliary power up here. And it's going to come to these terminals. Then we have A positive and negative. This is the class A return. We're not going to use that. We're just going to do class B. And then these are AB negative and AB positive. So this would be the class A send to come back to the class A return, or just the class B output. And we're going to use class B. You don't have to do any setting changes or anything to tell it if it's class A or B. It picks that up automatically. So I'm going to set that out of the way. First thing I'm going to do is I'm going to take my resistor and I'm just going to kind of bend it into a horseshoe shape so I can land it on output 1, positive and negative. Because what's going to happen is I'm going to come out of that AB positive and negative. I'm going to land on input positive 1 and input negative 1. And if this panel is ever in trouble, which if I were to turn it on today, it would be, 1, because it's bad, came back from the field as a bad panel. But 2, we know we have that open NAC circuit on NAC 2. There's a relay in here that can physically disconnect and connect the circuit from input to output right here. So if it's in trouble, it disconnects that, which disconnects the module from its end-of-line resistor. And that's how we know when this panel is in trouble. Now I'm going to have to make a couple jumpers here. So y'all have to be bored and bear with me while I strip some more wire. And so this wire that I'm stripping back right now, I'm going to use it as my auxiliary power over to my external power in on my control module. Also, if you have a water flow bell that you're powering off of an auxiliary circuit and then switching through a water flow device or a addressable relay, it would land on these same terminals that I'm about to land this wire on. So these are going to land up here and they're going to come over and I'm going to make it bend here. Take this and slip this into these terminals. And I'm going to hold this here because those are the standoff post or what this is going to mount to. Right there where my thumb is, that tells me that's about the length of wire I'm going to need. All right, so on this control module, I've landed on these top 2 terminals. Negative is on top, positive is on bottom. So I just corresponded the red with black. The same is true of this power supply. The negative is the top screw, the positive is the next one down. So that should line up pretty well. And then I have to make an almost identical jumper so that I can come from over here, this corner of it, straight into that input. And this is the same basic principle that any of these conventional type power supplies are going to need wiring up. They're going to have some type of way of triggering them. You're probably going to have some kind of sink unless it's a really small building that only takes 1 power supply. And doing it with these control modules is nice because it supervises for any troubles you may have, while also being a control interface. So you're not needing multiple parts. You don't have to run a NAC trigger wire all around the facility, and then whenever it goes into trouble, it just says NAC trouble, and you go from power supply to power supply to power supply. That might be hidden in obscure closets, and you have no idea where they are because it's quite possible that your company did not do the initial install, and so you have no idea where any of the power supplies are. So you're going around just looking and hoping to find it. And then when you finally do find it, it turns out it's just a battery trouble because no one's changed the batteries in 7 years because no one looked inside of the closet, in a closet, in a closet, in a closet. But of course, that's where they put the power supply, where it was impossible to find. By using the addressable control modules, we still get all the supervision possibilities, but now it adds the ability to describe where it is, just like we can describe where a smoke detector is. So we can say closet in classroom 232, power supply trouble. And then you go straight to classroom 232 and you look in the closet and oh, look, there's the power supply that's in trouble. And you saved a whole bunch of time and headache trying to find this power supply. So again, here's my control module. Now I came out of the bottom 2 terminals because that's my AB terminal. So this is going to be my class B supervision circuit. And it's going to come over here to input 1, positive and negative. And I'm making sure to keep positive to positive, negative to negative, because that is important. Making sure the wire is all the way into the screw terminal as I tighten it down. And do the same with my auxiliary power up here. By the way, make sure you don't get these crossed if you're ever working on one or installing one, because it will fry the control module. If you send auxiliary power into the wrong terminals, it won't work anymore. And yeah, yeah, you'll have a bad control module. So then I just fold in the little bit of excess wire. I put enough excess wire on here so I can fold it out and I can work on it so it's serviceable. But you can just fold it in and it should line right up. So now we have everything about the power supply wired up except the SLC. And that comes over here. It bends at that 90 degree just like the others have. And then I like to kind of bend it out so it can sit back and then just hit those terminals. So slide that right out. All right, so I cut that one back a little further than I normally do, but it'll be okay as long as the copper's under the screw terminals. So you can see that module's a little crooked because I've only got one screw holding it in right now. So let me see if I can get that second one in without completely wasting everyone's time. Screw it. Not going to worry about it right now. So the only other thing you have to worry about with this, make sure you do your address on your control module. So I'm going to make that one module 1. So now it's addressed. When we go back to the panel and we put it in, we'll say control module 1 is the FACP in Keith's office, or not the FACP, the FCPS in Keith's office. And anytime it has a trouble, it'll direct people directly to right here, and your panel's trimmed out. So like I said, if you had a sprinkler bell you needed auxiliary power for, you'd grab that off these 2 terminals. Ideally, we would need to go through and troubleshoot NAC circuit 2, find out why it's open. Oh, and your batteries would go down here. I'll probably do something sometime in the future on parallel versus series circuits, and at that time we'll address how to wire up batteries. But for now, here's the battery jumper. It plugs in like that, and it would attach to the batteries that sit down here. The only batteries that fit inside of this cabinet are the 7 and 8 amp hour batteries. The 7 and 8 amp hours are the same size on the outside. If you need something larger, which you really shouldn't on these panels, you would have to have a remote battery box, and you would have to make jumpers that went down, connected through conduit down here to the other box. And that box would have to be big enough to house something like 12 amp hours or 18 amp hours. But again, with this power supply, you should never have needs that large. Yeah, so that's basically it. If y'all have any questions, I'll be happy to answer them. If you want to go, I just looked at the time and realized this took even longer than I thought it would. So I apologize about that. If y'all need to get going, I understand. Thank y'all for being here.